here with lesson 2.2. Key questions for this lesson are: how does using vectors help us to think about and describe forces? And what sort of skills are needed to do math on vectors? As we saw in our previous lesson, we could represent forces with vectors. Vectors are symbolic representations of things like forces. Vectors have both magnitude, that is a certain size, as well as a direction. So because they have those two things, arrows represent vectors very well. The length of the arrow can show us the size of the vector, and the direction that the arrow points shows the direction that the vector is acting in. When vectors act together, they can add, and in the case of the previous picture we saw two vectors that were pointing in opposite direction. The result in that case was no net force, or a zero sum. And we can see that right here, that when you're combining vectors, it's quite simple to add them when they are in parallel to one another. That is to say, in the same line. If they are in the same direction, they just add together. If they are in opposite directions, they subtract. Here's another example. We've got Nellie Newton hanging around here. We see there's two vectors representing forces. One points down, that's Nellie's weight. And supporting Nellie is an upwards support force of 300 newtons. That is the tension in the rope. If we add another rope, then we can see two vectors. Distributing her weight in two different ropes isn't going to change the fact that you need 300 newtons to support Nellie. So as you can see, 150 newtons on the rope on the left, 150 newtons on the rope on the right. There's no difference really. They add up to 300 newtons either way. In each of those examples, the force vectors were parallel. They were in the same line. They weren't in the same direction, but they were in the same line. I'm going to now talk about vectors that aren't in the same line. We need to use what's called the parallelogram rule. Here we see we've got a vector pointing upwards and a vector pointing to the right. The resultant vector is the addition, or the sum, of these two vectors, and to find it we use a parallelogram. We draw in these lines here and here, which are parallel to the vectors that we were given, namely this upwards vector and this vector pointing to the right. The diagonal of this parallelogram, which in this case is a rectangle, is what we call our resultant vector. In the special case where the upwards vector and the outwards vector are equal in magnitude, or that is to say size, we have a special case where we just have to remember this number. The resultant vector for that special case will be the square root of 2 times whichever one of the vectors. This is just a property of squares or of geometry. It bears mentioning though, because the textbook problems try to keep the math fairly simple, and so they'll use simple examples where vectors like these here are equal to one another, and that way you just have to recognize that and be like, oh, okay, that's That's easy. I know how to do those. You don't have to get bogged down with the math. Let's apply the parallelogram rule to a circumstance here. I'll read this. When Nellie is suspended at rest from two non-vertical ropes, is the rope tension greater or less than the tension in the two vertical ropes? You needed to use the parallelogram rule to determine the tension. Earlier we saw a picture where Nellie is suspended by two vertical ropes. Here the ropes are at some angle. We want to try to figure out what the force is, or the tension specifically, is in these two ropes. Starting with our initial picture, we can add some vectors in. We know that there's a 300 Newton force going down. So there has to be a 300 Newton force going up, distributed in the two ropes. The picture then representing the upwards force can be represented by two vectors. Drawing in a parallelogram for those two vectors gives us a resultant vector as shown, which is diagonal to the two vectors that we have drawn. As the angle of our two ropes, or I should say the distance, as the distance increases, the angle increases. As we have a fixed 300 newtons going up, as the distance increases, we're going to see that the force in each rope will increase. Here, it may not be obvious in this picture, but wait till the next one. We can see that we have a force larger than half of what the 300 newtons is. This one's more obvious. You can see here clearly the length of this vector is even longer than the 300 newtons that come from her weight. Alright, that's a constant. But what isn't a constant and what changes as the distance of the ropes increase from one another is this vector here, that length of it. What we can conclude from this is that if you are taking a piece of rope and hanging it vertically, that rope that can hold on to you wouldn't necessarily hold on to you, or in other words, it would break if you tied it between 2 points like this and then hung on to it. As you saw in the previous slide, the force vector increases dramatically when we take and move those 2 points away from each other. Let's have one more look at this. Which child is more safe on these, on the swing set? Is the child in purple or the child in pink? What do you think? As you look at this and apply what we learned about vectors, which swing is more safe? As you ponder that, I'm not going to give the answer to you. I'm going to have you take a look at that question on the lesson that follows. Make sure you take the little quiz. That's it, folks. That's the end.